so we're going to take a look at section 7.1, which is our introduction to decimals. And as we're taking a look at these decimals, the first thing I want to talk about is the language that we use. The word decimal comes from the word 10, DEC, decimal, that's our decimal base. This is a base 10 system. And the language we use has to do with the placement of each of our values. So I'm going to do some of the place values, and we're going to talk about which of these places names are. All right, we'll do 5. All right, so if we start to the left-hand side of the decimal place, as far as I'm going over here left, what place value is this? That's the tens place. And the place value here is the ones, or sometimes you'll hear it called the units place. Either of those is fine. When you're reading language with the decimal point, what do you say when you hit the decimal point? We don't say point. We do that a lot now, or we'll say dot because we use the internet, right? The word dot. But there's actually a math word to say. Word and I have distinct memories from about 2nd grade saying something like this number and saying 736, and my teacher saying you can't use the word and there. Okay, so the word and actually mathematically means the decimal point. So when you see 736, that's actually 736, and there's no word and in there. So that and, that decimal point actually has a, or that decimal point actually has a word that goes with it. What's that place? That's tenths. And it's got that THS on the end. What's after that? That's hundredths. Next. Thousandths. And then 10,000ths. And the last one, that I've got up there anyway, will be what? 100,000ths. All right, so I bring that up because when you see numbers like this, what you're probably used to saying is something like this. 32.4236. For some people, they say point, they'll say dot, which they're saying. And we'd like to be able to say that correctly. Well, we're going to be able to say it correctly, whether we'd like to or not. So let's start with the first part, because we say that right all the time. The 3 and the 2 and then the dot. What do we say? 32 and. So let's write that down. And there is a hyphen between the 30 and the 2. So this is 32, and then their decimal point is the word and. All right, the number after that, the way we correctly say it is we say it as, we'll start out by saying it as though it's just a number standalone, 4236. So what would the number 4236 be if it was all by itself alone? And that's how we start, okay? So we say 4,200. Oh, I don't need that hyphen there. I didn't think so. 200. We have next 36. And after we say the number part of it, we indicate the place value that that's in. And that's based on the last number. What number place value is the 6 in? 10,000ths place. So this is 4,236 10,000ths. Okay. Yes, I missed it. I added it in place I didn't need it, and I missed on that one. Thank you. And then 10,000. And just like we'd like to be able to take the number and write the language for it, or be able to say it properly, we want to be able to go the direction as well. So if we have the number, or somebody said to you the number 536 and 36 thousandths, what would that look like as a number? So let's start with the part before the decimal. What number am I going to write down? Just tell me the digits I'm going to write down. 5. 1.536, and then there'll be a decimal point. Okay, so Lauren, why is it 0.76? Right, so the last word here tells you, well, it sort of tells you where the last decimal point has to be. The last non-zero number anyway has to be. So that, in this case, is a 6. So the 6 will be the third place. And then I need the number 76. So that would be one place over, and then there would have to be a 0 in the tens place in this one. So far, so good? All right. All right, base 10 is something that we work with in Math 1. So some of you have had some exposure to that. And you've been exposed to it in lots of places anyway before. But you might not have thought about it in terms of the decimal point afterwards. So let me do those same 5 that I had over here on the last slides ago, I guess. And the base 10 expanded form, this is the tens place, right? And this was the ones place. This we said was the tenths place, and the reason it's tenths is because it's worth 1/10 of a whole, which is actually a fraction. So that place actually corresponds to the fraction 1/10. And the next one corresponds to what fraction? 1/10 squared, which is 100. So it's the hundredths place because it's 100th of the value. And this one is 1/1000, it's 1,000th, because it's the thousandths place. And then keep going, so this is 1/10,000th, and this is 1/100,000th. And your book does a couple of different things on this one, but please follow what I'm showing you, and I'll tell you why after we do it, that it makes more sense to do it this way from my perspective. We're going to take this number, 103 and 3/100ths, right? And we're going to write it in expanded form. So expanded form, and this, again, this was the tens place and ones place, means that you take each digit and you write it multiplied by its place value. So this number 1 is in the what place? The hundreds place. So we want to write this as 1 times 100. We're going to write the zeros so that we don't lose any of our place values. So I know that this number is 0, but I'm going to represent it. 0 what? 0 times 10, so it's 0 tenths. Not tenths, but tens. And then I have what? 3 times 1. And again, I realize that when I multiply 3 times 1, it's just 3 to 1. But the 1 is the place value, so when I represent it there. I don't need anything to represent the decimal. So we're going to move past that. It's just the place values. The next one's another 0, but it's 0 what? Times 1/10, because it's 0 tenths. And then the last one is 3 times 1/100, 300. So what this visually does is it takes each number, each value, times the value of where it's located. Because the 3 makes a difference on where it is, right? Am I going to give you $30, $3, 30 cents, or 3 pennies? It matters where I put the 3. And this writes it out in a way that you can see all those places with their value. Let me show you what your book does, and there's nothing wrong with it, but what it does is it sort of hides the whole purpose behind what we just wrote. Your book will do this, and you actually alluded to it a little bit, Kayla, before. It will take each of these and it will write them as a power of 10, and that's great. We can write them as a power of 10, there's nothing wrong with it, but it really hides what's happening. Look at the back of the book on this problem. It's going to write down in blue. If this were in the back, this is what it would write in blue. And there isn't anything wrong with it. It's just that you look at that and it doesn't really mean anything in how you think about numbers. That's it. I don't think of a penny as 10 to the negative 2, do you? But I definitely do know that it's 1/100th of a dollar. Right? 100 pennies makes up a dollar. And that to me makes more sense. Because that's how we think about money, for example. Okay, so the blue part's what you're seeing in the back. I don't want you to do the blue part. I really don't. I want you to just write what we did in black. that's actually representing in the way we think about values. Right? So that's what this is talking about down here in red too. All right, a decimal square grid. So this kind of goes back a little bit into some of the pictures that you were asked to do on your test when you were talking about fractions, except that this is doing it for decimals. So a decimal square grid is a grid that's 10 by 10. So it's 10 wide and 10 long. Okay. And this distorts it some. But what we want is we want to split this into 10 rows and 10 columns. Okay, so on your paper you can do that. I'm going to do my best to do it here, and we'll see how well I get it. About 10, that's good. So we've got a 10 by 10 grid. There's 100 little squares in there, right? And what we're doing is we're supposed to represent this for the number 23 hundredths. So the whole square, the big rectangular square, however it is actually 1 unit. And it's split apart into how many pieces? 100 little pieces, right? And each one of those pieces is of size 1/100th. Right? Because there's 100 of them that make up the whole picture. So if I want to have a diagram that shows 23 hundredths, what would I do? I'll show you 23 of them. So on your paper, and you might as well do it in a way that's easy to work with, right? So there's 10 of them all at once. Here's 10 more of them, and then I need 3 more after that. And that's what I would do for 23 hundredths. Okay. So it gives you a picture. You can look at this and you can say, oh, 23 hundredths. Well, it's not very much of a whole. That's one of the things you can assess by looking at that, right? It didn't cover much of the diagram. I've got a lot more left over than I had originally to start, than I colored in. Those kinds of arguments based on a visual picture for them. All right, so a rational number in simplest form a over b can be written as a terminating decimal. Okay, in other words, we can turn a fraction into a decimal that stops. That's what it means to say terminates. It stops. If and only if, when you take the fraction and you reduce it, the denominator has only factors of 2 and 5. Okay. So the first thing you have to do with any fraction to use this theorem is make sure it's in reduced form. And you guys know how to do that, right? Many of you did it all on your test. Many of you have done it in the homework, and you've done it far longer than that. You know how to reduce fractions. So I want you to write that on your notes. Make sure you reduce the fraction. That is the most common error when I ask this question for students to do, is they forget that none of this works if the fraction is not reduced. At least it potentially won't work if the fraction is not reduced. So once the fraction is reduced, and both of these are, what we do is we look at the denominator and we factor it. Okay? There's lots of ways to do factoring. I'm going to show you 2 of them. Some of you have for other classes have already seen my 2 ways of factoring. But you may not have seen both of them depending on who you've had for other classes and whatnot. One way that most of you probably seen is factor trees. Everybody knows what factor trees are, right? Okay. So let me do the 8 with a factor tree. So if you do a factor tree, you put the number on top and you draw branches below it. And what you do is you take any 2 numbers that multiply to 8. And this one's not real exciting. It's too important. We don't have any options, right? They're just grab stuff to try. So we put 2 and 4. If the number's prime, and prime numbers are numbers that don't divide any further down, then you're done with that branch. So the 2 branches done. But 4 is not prime, so we do it again. And that's 2 and 2. So what we noticed then is at the end of the branches, we could write 8 as 2 times 2 times 2, or if you prefer, you can write it as 2 cubed. Either of those are fine. The question, though, had to do with whether or not we could write this as a terminating decimal. And this theorem up here says that if the denominator contains only 2's and 5's, it doesn't have to have 2's and 5's, but it can't have anything else. You have 3 down there, or 7 down there, or you can't have anything else down there, just 2's and 5's. And if you only have 2's and 5's, then we can take that number, and if you took any number in your calculator, you can see it will be a terminating decimal. Will 3/8 be a terminating decimal based on this description? Yes. And if you put it in your calculator, and go ahead if you'd like, you can see that it's going to work. It's really going to give you a number that stops, terminates. So this is a yes. Okay. Determine if it does. So did it work in your calculator? Yes. Okay. Item number 2 says write it as a terminating decimal. So here's the deal again. To write it as a terminating decimal, you can verify this with your calculator and get that. Okay? If you were teaching this in, say, probably 4th grade, I'm guessing. Okay? If you were teaching this in 4th grade, your students are going to still tell you what my daughter tells me, that calculators are cheating. Okay? We kind of tell our kids that. I mean, that there are certain things that, at appropriate levels are not considered appropriate to use, right? Calculators are not appropriate to use for this, because this is not what you would have your students do. So what I'm about to show you is how you would be teaching this if you were teaching it to your students, and I want to see that you did it that way. So, do you remember how you changed 3/8 into a terminating decimal without your calculator? Yeah, you just use long division. So, if it's been a while since you've seen it, the 3 goes underneath the division sign, and the 8, what you're dividing by, goes on the outside. And we're going to put a decimal point in a 0 because 8 doesn't go into 3, okay, evenly. But if we consider the 3 in the decimal as the number 30, we can ask ourselves that question at that point. How many times does 8 go to 30? 3. The 3 goes above the 0 and the 30, and the decimal point goes above where it is as well. And then we take 3 times 8, and 3 times 8 is 24. We write down 24 and we subtract. What's 30 minus 24? 6. So we're not done because 6 is not 0. So we add another 0 to the 3.0 at the top. So we've got 2 zeros, and we draw that 0 down here by the 6. Then we ask ourselves again, how many times does 8 go into 60? 7. This is why learning your multiplication facts is really important, right? For those features. And how many times, or I'm sorry, what is 7 times 8? 56. And I subtract and I get, oh, I wrote 54. Right. I was ready to write my 4, I think. All right, if I subtract, I get 4. All right, so then that's still not 0, so I do one more 0 here. And 8 goes into 40 5 times, and it goes in evenly, right? And once I put this 40 down here, you see you get a remainder of 0, so then you're done. Once your remainder at the bottom of 0 is out, you're done. And you know it will, because the theorem said so. So if you've got another number, one of two things happen. Either you subtracted or multiplied wrong, which is a possibility, or you just need to go another step to zero out. And you can check your calculator, that's fine, I don't have a problem with that. But you can't do the work in your calculator. With me? All right. Let's do the same thing on 5/12, but I'm going to show you another way to do a factor tree, or a version of factoring. So another way to do a version of factoring using this 12 is to write the 12 with a divisor over it. And what you really do in this method, really, is you look for the smallest number that divides 12. So you don't just look for any random number, you look for the very smallest number, and the smallest number that divides 12 is 2. Okay, and it'll go in evenly, so we're not going to get any remainder, so there is nothing that will happen below the 12. The 12 is the bottom of my stack. And then if I divide 12 by 2, I get 6, which I write on top. And you know that looks just like division, no problem. But you're not done because 6 isn't prime. So we write this sort of stacked on top of this, and we divide again. Again, the smallest number. So what's the smallest number that goes into 6? 2. So we write this out here, a 2. And 6 divided by 2 is 3. So all of my branches are in order, which is kind of friendly. And for a larger denominator that's got more complicated pieces to it, that's friendly to have it in order. Not only that, but the nice thing about this as opposed to a factor tree is that when factor trees do get long and complicated, it's really easy to lose one of those 2's in the middle of the tree. It happens a lot. So this one keeps them all in the same spot. I don't care which one you use. It doesn't matter to me in the slightest. But these are a couple of different ways of looking at them. All right, so looking at my factors, 12 is now 2 times 2 times 3. Can this be written as a terminating decimal? No, why not? Because it's not just 2's and 5's, I've got a 3 involved, right? And if you grab your calculator, take 5 divided by 12, see what happens. It doesn't stop. It actually is another kind of number called a repeating decimal, isn't it? We'll get to repeating decimals later. It's a repeating decimal, yeah. All right. So this one's answer is no. And since it's no, we don't have to write it as a decimal because it doesn't exist as a repeating decimal. So the answer no is your favorite answer. It means you can stop doing the problem. Right? You're done. You can stop. So that was a friendly one to start with. All right, so I know many of you know how to compare decimals because that's what you tried to do on my compare fractions question test. But we're going to actually learn it now. And so we're going to talk about comparing and ordering decimals. So when you compare and order decimals, and here's a mix of ones, you line the numbers up by place value, and you read from left to right to find the first difference, and then you compare the different digits. So I find it easiest to work with these because these are very similar numbers, agreed? This isn't like the 0.68, 0.71, 0.72, or whatever they were on your test. These numbers are really similar, and there's a lot of weird things going on that looks very similar from number to number. And so I find it easiest to line them up on top of each other, hence the phrase lining them up that it's talking about. So that each of the place values is above the others, above or below where it actually is supposed to be. I have 13.49183, and then 13 and 49,199, 10,000. So did I get them all written right? I think so. All right, so looking at these values, they're lined up. And what is the place value where you notice the first difference? The thousandths place. So up until here, they match on the left of that line, right? So the first place you notice them different is with the second number, and it's a 2. The rest of them all match still. I don't have a comparison finished for those parts. But what does that tell you about my second number? It's the biggest because the 2 is larger than 1, right? Yeah. So this is my largest. So there's my largest. We'll write them in order in a minute, but that's my largest. All right, all the ones match. So then I go to the what place? What's next is the place value? The 10,000s. So I'm looking at these 3 numbers. 2 of them match and 1 of them is different. The different one is the third one. It's got an 8 there. What does that tell you about that value? Smallest, because that 8 is smaller than the 9s. So this one's my smallest. So this one says least to greatest. So least, smallest would be number 1, greatest would be number 4. Right? So if we're ordering them from 1 to 4. We have our last 2. The last placeholder that we have on the screen is the, what place? What is this? This is the 100,000ths place. I know I circled it and I circled the 3, but I already used that number. What is the only 2 values I'm comparing right now? the 0 and the 9, the top number and the last number, because they're the only ones I haven't identified anything about yet. So comparing the 0 on the top, and that is a 0, right, with the 9 on the bottom, what does that tell you? Which one's smaller? The top one is smaller. So this one right here is, I'm going to say smaller, because I already said smallest a minute ago, and this one is larger. All right, so where should the number 2 go? On the top. And then that means number 3, the one left is on the bottom. So this is the kind of work that I would expect if you were looking at this, to show your comparison. It may not look exactly like that, and that's fine. But something that actually shows that you're looking at plate size and you're making assessments on 2 of them at a time or whatever in comparison to each other. And then when it says order these decimals, you can do one of 2 things. You can either write them in order with commas, which some of you did when you were working with fractions in the last test, or you can write them in order with the less than or greater than symbols, depending on how the problem is asked. So I'm going to use the symbols because some of you didn't think to do it that way, which is fine. But I'm just going to show you how to do that with this particular one. So I'm going to list the smallest one first, which is 13, and then the 49183. That's my smallest. And I'm going to put a less than sign. Problem number 2, or value number 2 is the top one, 13, and then the 4919. And then I have number 3, which is the bottom value, 13, 49199. And then my largest value, which is 13 and 492 thousandths. And you don't have to use the symbols, you can use comments, that would be fine. Because they actually told you least to greatest. Be careful, you're really doing least to greatest, but greatest to least. Common mistake too. All right, one last problem in this section. All right, what is the meaning of the word tithe? You use it all the time in church. Anytime somebody starts talking about it, you get a little uncomfortable because it affects our money, right? What does tithe mean? It means 10%, right? So sometimes people use that word and they sort of mean just some amount, random amount of giving, and that's not what it means. It actually has a real concrete meaning, and it means 10%. Okay, now I'm going to write down in a little bit different way, but related, but without the word percent in there. Okay, and this is actually, I know this is not your best resource, but it's okay on this. From Wikipedia. This means 1/10. Which is the same as 10%, right? We haven't done percents yet, and I get that. But 1/10, okay, of something. All right, so 1/10. Let's write it a couple of ways. How can we write 1/10 as, let's do a decimal first. How can we write 1/10 as a decimal? 0.1. Well, we could. Either 0.1 or 0.10 if you'd like. Yeah, those are the same. How can we write it as a fraction? That's 1/10. And literally, if you were doing this with your income, for say, for your church or whatever, there's several different ways you could do that. So somebody tell me one way you could do it. What's one way you do it when you're figuring out your tithe? Okay, so you can grab a calculator or whatever, you can multiply physically by 0.1. What else could you do? You could just move the decimal point 1 to the left. Yes, you could. There's one other thing you could do. You could divide by 10. And all of those are the same operations, but they're thinking at it from a different perspective, right? This whole idea of moving the decimal point, that's an algorithm. That's a process somebody told you when they said, well, when you multiply by 0.1 or when you divide by 10, all it is moving the decimal point. That's an algorithm approach. When you're taking this multiplication, this division approach, that's something a little bit different. But you get the same answer in either way to do it, right? All right. I think I'm good with whatever.